Welcome to this lesson about the hypothesis on the variance. Now we are going to check the variability of a population. So previously we have seen how to check the mean value, which indicates the central tendency of the population. So we know that any population is mainly described by two parameters. We have the mu or the mean value to describe the central tendency. Also, we have the sigma square or the variance of the population to describe the variability within the population. So we know this is our population. To perform the hypothesis and testing of hypothesis, we take a random sample of size n. For example, at random time or random manner, we take random sample of size n. We can test for the central tendency of the population, or we can test for the variability of elements inside the population. To test for central tendency, we have seen how to test for the population mean, which is mu. We have seen two types of test. We have used the z-test or the normal distribution test when we know the sigma square or the variance of the population. But if we don't know the variance of the population or sigma square, we had used the t-test or the student t-distribution test. So this is for central tendency or hypothesis on the mean value. Now we are going further to test the variability within the population. So we are mainly going to test for the variance or sigma square, or we are going to test for the standard deviation sigma. In fact, the methodologies are exactly the same and there is no difference to test for sigma square or sigma, but we will concentrate and focus on how to test on the variance or sigma squared. So previously we have used the normal distribution or z-test, and we have used the student and t-distribution for the t-test. Now we are going to use another distribution which is called the chi-square distribution to perform the chi-square test on the variance value. So now let's look what is the variance of a population. In fact, the variance of a population is only a measure of the variability or the spread of the data or values around the center. For example, this is a signal which present values for a specific for example specific voltage or something like this. We have the center here, this line at the center. For example, this is the mean value, and we have the values of the signal are spreaded above and below the center. So the more the value are spreaded or variable above and below the center, we say that we have larger variance. For example, here below we have two population. We have population A and population B. We have the population B. The values are centered and focused more around the mean value, but the population A is more spreaded, and the width of population A is larger than the width of population B. So we say that the variability or the variance of population A is larger than the variance of population B. So this is only to understand what is the variance of a population. So after we have a sample with size n from the population, now we can perform the test, but before that we need to calculate the sample variance. We have this equation before for the sample variance. We know this is the simplified equation for the sample variance. Firstly, we need to calculate the squares of each element in the sample. Here we subtract, this is n, which is number of samples, multiplied by the square of sample mean. We divide by the degrees of freedom, or n minus 1. For the population, we have the symbols mu for mean, sigma square for the variance. For the sample, we take the sample at random manner with size n. Now we perform the test for variability using the sample variance and using the chi-square distribution. So the same methodology, we are going to use the test statistic to test our hypothesis. Now the test statistic is called chi-square. So we are going to use the chi-naught square point as a test statistic. So the chi-square, or the test statistic for the variability test, is chi-naught square, which is equal n-1 multiplied by the sample variance divided by the population variance, or the hypothesized population variance. So here below we have the hypothesized population variance, above we have the sample variance, and n-1 is the degree of freedom. So degrees of freedom is n-1. Also, we perform our test on the variance at a specific confidence level, which is 1 minus alpha. For example, if alpha is 5%, our confidence level will be 95%, which is the most common and popular confidence level to perform tests of hypothesis. So this is the chi-square distribution. We notice firstly that the chi-square distribution is not symmetric around the mean value. We have seen the normal distribution and the student t distribution are symmetric and even around the center or the mean value. But chi-square distribution is not even and is not symmetric around the center. Also, we have seen the normal distribution and t distribution can take negative values, but the chi-square distribution only in the positive side, from 0 to positive infinity, because the variance values are always positive. There is no negative values for the variance. So this is the chi-square distribution. We are going to use the chi-square distribution to perform our test of hypothesis. So suppose now also we have two-sided test. We will divide alpha into two sides. To the right we have alpha over 2, and to the left we have alpha over 2 for the area under the curve. So in the middle will be the acceptance region, and here this blue area is rejection area, and here we have the blue area is the rejection area. So we are going to test our hypothesis based on the chi-naught square and the critical values for the chi-square. We are going to reject the null hypothesis only if our test statistic, which is chi-naught square, is larger than the critical value here, which is this value. So if chi-naught square is larger than or fall in this area, we'll reject the null. Or if chi-naught square is less than this value, or in this area, shaded area in blue, we will also reject the null. But if chi-naught square falls in this acceptance region, we are going to fail to reject the null hypothesis. So now suppose we have an example to illustrate these facts. So we have a population. We are assuming, or our initial assumption for the variance to be 7.0. Our null hypothesis, we suppose, or we are afraid that the variance has changed to be not 7. So we have the null hypothesis, sigma square equals 7. We have the alternative hypothesis, sigma square does not equal 7. Suppose now after that we have taken a random sample. The size of the sample was 15. So we have taken 15 elements from our population. So these are the values of the 15 elements. So we are measuring a specific property. And these are the measurement of the specific property. Now we are going to test for the variance of this property among the population. We are also going to use the 95% confidence level, which is the most popular confidence level. So this is again our sample, and this is our measurement for the specific property we are testing. Firstly, we are going to calculate the sample variance. Using this equation, we directly can compute the sample variance. We found that the sample variance is 10.23. So simply also we're going to calculate the chi-naught square, which is our test statistic. So we have n to be 15, so 15 minus 1 we have 14. The sample variance here we have 10.23. Here we have the sigma square, which is the hypothesized variance of the population, which is 7.0. So now we calculate chi-naught square to be 20.46. So with the same methodology, here we will reject the null hypothesis if chi-naught square is larger than the critical value here, or chi-naught square is less than the critical value to the left. Now this is the table of chi-square distribution. So here in the column we have the value of V, which is the degrees of freedom. We have 1, 2, 3 until 17. We know that degree of freedom is sample size n minus 1. Here we have alpha in this row. So alpha in fact only is here in this distribution is the area under the curve from the point until positive infinity. So alpha is the area under the curve from the point and to the right side from the point. So what are our critical values? We have firstly chi-naught square alpha over 2, because we have two-sided test. So we divide alpha into alpha over 2 and alpha over 2 to the left, or 1 minus alpha over 2, so we have the area under the curve to the right of the value. So our critical values are when the degrees of freedom is 14, because the sample size is 15, so we have the degrees of freedom to be 14. So we are going to use this row of 14 degrees of freedom. Now we are going to use the critical values for alpha over 2. So the right critical value will be when chi-naught square has an area under the curve to the right, which is 2.5% or 0.025. So here we have 0.025 as the area under the curve. We are going to look for the intersection with 14. So we have the first critical value for chi square to be 26.12. So this is the first critical value, which is the right side of the two-sided test. Yes, because here we have the alpha 0.025, which is the area under the curve under this critical value, in case we have the degrees of freedom to be 14. So we have the first critical value 26.12. Also the second value is chi square when the degrees of freedom is 14 and the area under the curve is 0.975. This is because we have the acceptance region to be 95%, and to the right we have also 2.5%. So to the right of this left side critical value we will have 0.975 area, or to the left of this value we will have also alpha over 2 or 2.5%. So if the right area under the curve to the left critical point of chi square is 0.975, we are going to find the intersection with 14, which is the degree of freedom. We will find that this value is 5.63. So now this is the left critical point, which is 5.63 as we found from the table. This is the right critical point, which is 26.12, which we found from the chi square table. And this is chi-naught square, which is our test statistic, which we found from our calculations. So we found that the chi square we found that the chi-naught square, which is 20.46, lies in the acceptance region. So if chi-naught square falls in this area, this is the rejection area, or in this area, this is also the rejection area. But in between, this is the acceptance region, so we are going to fail to reject the null hypothesis. And therefore, the population variance at 7.0 should be considered an change. So we consider the variance of the population to be unchanged at 7.0 for the sigma square of the population according to our test. We notice that the conclusion or the result of our test depends on the confidence level we choose, because if we change the confidence level, this value will change and maybe we have different results. But here, for the confidence level of 95%, we have failed to reject the null hypothesis, so we conclude that the population variance is still unchanged at the value of 7.0.